So let me just recap a little bit about teleportation and dense coding, just to remind you. So this is the process where, let's say, Alice gets a qubit, of course prepared in a state unknown to her, and the idea is to send that on a classical signal to Bob. So we have Alice here, and we have Bob here. And this is an impossible machine, we discussed that. This is a translation of classical information to quantum to classical and back to quantum. So in whatever way you do that, this is a measure and re-prepare channel, if you want, measure and re-prepare. And they're also known as entanglement breaking, which means you can never make this the identity. Okay, so but if you have also, in addition, a source of entangled states, which by themselves, of course, wouldn't be good for any kind of communication because it's just correlation, right? Then you can do it, right? And so you measure something here. So the typical situation is d-dimensional Hilbert space there, well, actually everywhere. And here we have d-squared signals. So I certainly won't go into the whole thing again, but just mention a few specifics. So there's dense coding. Or maybe super dense coding, which is exactly the opposite. So we have d-squared signals, and we have a quantum channel. We get d-squared signals out. This is a Hilbert space CB. And we have the same sort of entanglement assistance. Okay? So normally it's clear how to send d different signals over a d-dimensional quantum channel. You just prepare the input states in orthogonal states, and then you read out at the end with a projective measurement, so that's easy. But putting d-squared signals on is, well, usually not possible. Certainly if you don't have this entanglement assistance, it's easy to see that this is actually impossible without errors, and even with errors, the tough, hard bounds that tell you that you cannot do this sort of thing. So the entanglement actually helps to get more classical information across. And one of the results here is if the numbers are as written here, then actually, if they know how to do this, Alice and Bob, they also know how to do this by just swapping their equipment. This is a bit surprising because it's not obvious that this should be the case, and it's a result of the analysis that David gave in the last lecture. Okay, so this is actually the surprise that made me write this paper about all teleportation and dense coding schemes, where you see in the end somehow that this works. And to highlight that this is not somehow an obvious thing that can be proved in a much easier way, let us just discuss what happens. Let's say we take all these spaces d-dimensional, and we change this number. So actually, if instead of d-squared signals, we have more different signals that we can send and distinguish reliably, then the teleportation problem becomes easier. Because I just don't have to use all the signals, right? So if I have more signals that I can use for reliable transmissions, the problem actually gets easier. So increasing this number from d-squared to something more makes teleportation easier. But this thing becomes harder because in the end I'm supposed to distinguish all these signals, so I have the same resources, I'm supposed to code even more onto it. So when you change these parameters, one of the problems becomes harder and the other becomes easier. So they're not the same problem somehow, right? This swapping happens exactly when these numbers match. And this is the case that was analyzed in detail. But this is a reason why choosing exactly d squared signals is relevant. Okay? Then I would just like to discuss what teleportation isn't. Well, actually the term was chosen in the first paper, and when I saw the paper, as it appeared in the journal, I said, well, these are some kind of crazy people I don't have to concern myself with, right? The teleportation. We know that's fantasy and so on. So actually I didn't read the paper. And then a little bit later came the superdense coding thing, and I realized, oh, wait a minute. And then I went back and realized what teleportation was. So the choice of this word, teleportation, was, well, on one hand it was some stroke of genius because everybody was listening. And for a while we had lots of popular articles, each one with Captain Kirk and a whooshy picture of him being beamed around, right? So this confusion of teleportation with Star Trek type transporter was probably intentional. I think it was Charlie Bennett who did that. I'm not sure, but I asked him at some point, but I don't remember who it was exactly, or whether they came up with that together. I don't know. But it certainly changed the way quantum information was perceived by the public. So, because all these popular articles were harping on this teleportation thing, right? So, but actually, this is totally misleading, right? So, of course, you know that in Star Trek, the teleportation process, or the transporter, I think they call it, I'm not sure, I haven't seen so many in English. So the transporter was actually introduced in order to make the production cheaper, because when they had big landing scenes of Enterprise on a planet, this would be kind of tricky. It's much easier to just have a shot of the place where they go, and then whooshy whooshy, and then you have the people right there, right? So it's a simple overlay of two pieces of film, which is much easier to produce than a big landing scene in whatever way you do it, right? Wouldn't be, well, yeah, in whatever way they do it. So this was just cheaper, and that's why they introduced it. Of course, it also has been a topic in various science fiction stories. It's somehow, for the narrator, it's a simple way to move people around, right? You don't have to worry about the journey, and these journeys are boring. So if you've seen Odyssey 2001 more recently, then you see how the perception of timing in films has changed. There's an endless scene where they just travel to the moon in a sort of airliner. Well, it's in space, but nothing is really happening, and it's utterly boring. Well, to modern viewers, it would probably mostly be boring. So, okay, so this is why Star Trek had beaming in the first place. So, but if you compare here, definitely in this teleportation process, there is no mentioning at all of moving matter around. Right? So in the place where they're beamed to, there is air, and afterwards you have the excursion team of Star Trek. Right? So there's somehow matter is being moved in these movies. This process here is purely informational. So Bob already has this particle, right? And he's doing something to the particle. It's the classical equivalent of the teleportation process is Alice is calling up Bob and telling him, take your penny and put it face up, because that is a way to determine the state of a remote object. And they could just use the telephone line and transport this information, and Bob would do the appropriate transformation. Right? So there's no penny that is being produced at the other end. No transport of matter. Then something that is frequently messed up is no superluminal. So you sometimes, well, this is not in Star Trek, right? They move faster than the speed of light anyway, so they don't care about that issue. In some of the popular accounts, what is being miraculous here is has something to do with instantaneousness. And that is definitely false, because you always need these classical signals. They have a certain runtime, right? So you could never make something appear faster than the speed of light would dictate, right? So there's no superluminal effect at all in this whole situation, right? Because certainly these classical signals are limited to the speed of light. Now, for a more interesting thing, so, I mean, if you look at this picture, what is being sent here, right? So you could think of this whole distribution of entanglement as something that is done beforehand, before actually even this unknown qubit or whatever is being brought to Alice. Before this happens, let us think of this entanglement already being distributed, right? And it's clear that at this moment, there's no information that had actually moved from Alice to Bob. Right? So the only thing that moves in this whole, or could move information here, are the classical signals. So it is actually quite natural to think that somehow the information about the quantum state are encoded in these classical bits. Right? So 2 bits for a qubit in the qubit case. The d squared would be 4. Right? So you could think about think of an eavesdropper intercepting this classical information that is moving around. Would the eavesdropper learn anything about the quantum state that is being transmitted? Well, what's your answer to that?
No.
No, it couldn't be, because this would be an interaction-free measurement. Right? I mean, this would be a measurement without disturbance. Right? So certainly we can copy this information and give it to Eve, and Eve would have no clue about what quantum state was being sent. Right? And because if we know already, if the overall thing is the identity, and that we do know, right? This is part of the computation, or that's the definition of good teleportation. So this overall thing is the identity. So whatever classical information is generated in the process must be non-informative. It cannot tell you anything about the state. When they change the state, the probability distribution of these outcomes will not change. Actually, the distribution of these signals is always, you can just check that from the computation, the distribution of these signals is always equidistributed. I mean, they're all equally likely, but the distribution, and this is no matter what the input state is. So the information about the quantum state, although it is in some sense transported by these classical signals, is not actually residing in these classical signals. This is the paradoxical aspect. Right? So you can read out the classical channel, all right, but this will not tell you anything. Right? And we know this principle already. Right? No measurement without disturbance. So what else? Suppose I copy that. How would I get? Now, suppose I had the following. That's the next slide. So here's another thing you might try to do. Try to prepare a state, this source. Let us think of a slightly more difficult source, which actually has 3 particles that are entangled with each other. Right? Well, especially with Alice's. Right? Alice gets 1 particle, and she has 2 partners, Bob and Charlie, and they each get one of these other particles. And the idea is that Alice is entangled with Bob in the same way as she is with Charlie, namely shares a maximally entangled state. Okay? Now, if that were the case, Alice does her measurement, right? And she gets this information out that this has nothing to do with Bob and Charlie. She just makes the measurement. So she takes the signals and takes one signal she sends to Bob, and the other she sends to Charlie. And she just copies that signal and distributes it. So Bob and Charlie would run they do their usual thing, and both of them would then have a perfect copy, which is forbidden. So what was wrong? Well, the assumption that you could make a source in which Alice would be entangled with Bob and Charlie in the same way, right? So that you have a state, let's say a D-level system, 3 D-level systems, so that Alice's particle is maximally entangled with Bob's, and also maximally entangled with Charlie's. And this is forbidden, and this is called the monogamy of entanglement. So if Alice is very highly entangled with Bob, she cannot be highly entangled with the same degrees of freedom with Charlie. Of course, she could just run 2 separate teleportation lines, but then she would need an additional state here. She would have to make a new measurement when she sends something to Charlie, and you would just have 2 separate teleportation lines, but then you're actually using up entanglement, right? So this is also true that in this process there is a sort of fuel, right? So the entanglement is used up in the process. So if I have a way to generate entanglement between Alice and Bob, this is very good. But if I want to send long messages via teleportation, long quantum messages, for every bit of quantum information that I want to send on this teleportation channel, I need a maximally entangled pair. And I cannot reuse that. There's no recycling of the fuel here. This is really used up. And this is the resource character of teleportation, which is why I think the whole section I call tasks and resources. Right? So resource here, entanglement is very clearly a resource. You need to have that in order to do the teleportation, and for every bit you need a new entangled qubit pair. It's still on the theme of comparison with Star Trek. So the largest system that has been teleported is probably a qubit so far. Maybe somebody did 2 or so. But basically, so teleportation has been realized in various labs the world over, but all these experiments have very few qubits. Now, this is very different in Star Trek. So, actually, the information needed to assemble J.T. Kirk with sufficient quality that he would walk away alive is staggering. Right? So, there's a fantastic amount of information. Of course, this whole memory content is just one of the little things that has to be done right in order that we are not actually killing the man. Right? So the real problem of Star Trek teleportation is the capacity of the computer. I mean, all this physical stuff is kind of, okay, it's difficult, right? And but we could roughly have an idea how this can be done, right? But the channel capacity necessary to transport all the information needed to assemble a human being at the other end, this is absolutely staggering. Right? So like all the libraries of the world plus extra. Depends on the accuracy that is needed, which is actually an unknown quantity. Right? So how precise we have to restore every atom and so on in order for the subject to survive and apparently healthy, right? We see that in the films all the time. Well, it's not clear how precise it has to be. By the way, one question is whether this is a quantum process. Right? This is something I definitely have to mention. So our teleportation is a quantum process. And there's an obligatory story about this. So the original idea of teleportation was exactly this, right? You make a copy of the. I didn't finish writing that line. So you make a copy of everything that is necessary to reassemble the person, and then this is somehow done by the transporter. And then some smartass came up with saying, well, but you couldn't know all the positions and momenta in J.T. Kirk's body, right? Because there's a Heisenberg uncertainty principle. So they came up, I mean, these techno blurb writers, they come up with something arbitrary, and then this is just put into the story. I mean, the technology isn't really the heart of Star Trek, obviously. Everybody who's seen the series knows that, right? The technology is just invented as needed. Right? So they did exactly that, and to counter this objection, they invented a gadget called the Heisenberg Compensator. And the ingenious answer of Gene Roddenberry when he was asked, well, how does this Heisenberg compensator work? He said, very well, thank you. So this is a sort of the obligatory story here. So, so this is actually a proper quantum process, and it is not hit by this objection that we can't know position and momentum because the whole quantum state is faithfully copied. No problem with that, right? But there is actually a problem whether the Star Trek process is a quantum process at all. They don't have a Heisenberg compensator. And this is shown by one of the episodes of the New Generation series, when Commander Riker gets left behind on a planet. It's an iron storm, right? So you see, sometimes when there's difficulties in beaming, you see the image appear and disappear and so on. So they have some iron storm stuff like that. And then they finally manage. And so Riker is back on board and they fly away. But in this iron storm, actually, there was a copy left behind. So one copy of Riker is actually back on the planet, and he gets pretty pissed because normally, as you probably know, they never leave any one of the central crew behind, right? If some of the minor character gets a speaking role, he's dead by the end of the episode. This is also a well-known principle. So they do lose some personnel, but never of the core team, right? So, almost never, right? Very rarely. So the Riker knows this, and of course he gets very, very annoyed. And then sometime later they meet up, right? So, and actually you have this guy that was left behind and bears a grudge against the whole Starfleet, and meeting the other guy who's quite happy and so on. So this is one of the stories, but this means that they've copied. So the process is clearly classical, right? So we don't. You couldn't make a copy with this process, right? Precisely because of this resource character of entanglement and so on. Right? So I'll explain that. So yes, but then also there is the channel capacity. I think this was pointed out by Sam Brownstein early on, that the really miraculous thing here is a computer And it also has to satisfy additional needs of the story makers. For example, we never see anybody going into quarantine. So they could contract all kind of dangerous diseases from the planets they're visiting, but they never have to be put into observation for that, because in the teleportation process, automatically the computer corrects for that. I find this fantastic. So, yes. Anyway, so much for Star Trek. Are there questions about that? Actually, who has watched more than 10 Star Trek episodes in the audience? Okay, so maybe I was talking to the wrong people. So anyway, so this is just don't confuse that. Okay, so let me come to the next kind of task that we have to discuss, and that is error correction.
Would you once more say
Yes.
about monogamy of entanglement, the contradiction?
Okay, suppose you could make a quantum state which has the following property. It's a three-party state, three copies of CD, labeled A, B, C. Right?
Mm-hmm.
And the property is if the restricted state to AB is maximally entangled, and the restricted state to AC is also maximally entangled. So the kind of thing that you need for the teleportation. Right? And if something like that existed, right, subjunctive, then you could actually split quantum information. So the monogamy of entanglement is in some sense the state analog of this no copying principle. Okay, so let's talk about error correction. So this is what we need when we want to communicate over noisy channels. So the classical analog of a noisy channel, let's take the prototype of a 1-bit channel, right? So you put a 0, 1 input, and you have a channel which could actually be physical transmission device, whatever, it doesn't really matter. And the way to describe this in the setting that we have, all the channels are actually probabilistically acting, so the probability matrix So, in the simplest case, you send a 0 in, and with probability 1 minus p, you get 0, and with probability p, you get out. Get 1 out, and the wrong one out. And the same happens at the other end. Actually, these two p's don't have to be the same, but this is then called a symmetric bit flip channel or something. So, okay, so this is a standard error-producing channel, and you could think of this as happening in some transmission line. So there's a certain probability that the bit comes out wrong at the other end. So what do? We certainly still want to communicate. So the standard solution is redundancy. Send 3 times. So what you do is you have your bit here, then you make 3 copies of it. Each one of them goes through one of these channels. So at the output we also get 3 bits, and we decode this by using majority vote. This is why I took 3 and not 2, because you actually want to know which bit to take. If you have only 2 and they have something different, you actually don't know which one of them made the mistake. Right? So, but if you take a majority vote, you get another 0-1 out. And obviously, in order to get it wrong, 2 channels have to make the mistake. Right? So if there's an error happening on 2 of the channels, the majority points in the wrong direction. Right? So, but you have a very similar thing, and the final error probability is then of the order p squared. So think of p as small. Basically, our channel is good. So p is small, and then this redundant encoding channel will have error probability p squared, which is much better, right? So if you think of 1% error probability, then we are in the 10 to the minus 4. Right? So this is actually a practical way of doing it. Of course, this is a big industry. Right? Error correction at all levels is one of the key elements in information technology. So even a CD player uses error correction of some sort. And of course, this is just the very simplest scenario, right? So of course, you could, various things you could do, and there's a whole theory about it. This is the channel coding theory of Shannon that tells you how to compute what you can achieve in the end. Right? With a given noisy channel, that could be more complicated than that. Okay, so, but why am I telling you this? There was a copying step here. Right? So we cannot just take this process and quantize it in some way. Right? So this is really a very bad idea because we don't have this copying mechanism. So we could, of course, copy some aspects of this, of our quantum state, but we would always mess up something if we start copying. Right? So, I mean, if we could copy the information in one classical basis, of course, like this, but then the conjugate basis would be completely messed up, and that wouldn't be helpful. Right? And this was pointed out very early on in the development of quantum information theory. Actually, the Shor algorithm and some other things like teleportation and dense coding and so on are basically zero error processes. So people didn't initially worry about the errors, but of course we have to, because if you want to ever build this thing, every device that we're actually using will produce errors, and we have to cope with that. And if you have computation with a constant level of errors, you're not really happy. Right? That's, for computation, it's slightly different. I'm talking here about errors in communication. So, but even there, it's this is an obvious problem. So therefore, it was actually a big discovery and an important step for this whole field that somebody came up with a way to correct errors. Right? And so there's a famous paper by Calderbank and Shor. It's maybe not totally the first, but I like the title. It's something like good error correcting code, quantum error correct code exists. Maybe with an exclamation mark, but you don't actually have to write the exclamation mark because it's sort of there, right? So at that time, this was an open problem, and precisely for this reason. So it was not clear at all whether you could do anything like error correction, and that, if not, this would have killed the whole field, right? Because somehow you have to find a way to cope with that. So this was a very important step for quantum information, and we'll have to approach that. Right? Now, this whole topic is like the classical counterpart, coding theory, channel coding theory for quantum information is worth a lecture on it in its own. Right? So I won't do very much of it, but I will certainly try to give you the basics. Right? So the quantum version should look like this. Well, now I have wavy lines for quantum information, and there is an encoder. And this would take some input signal and produce 3 output signals. Or maybe more, right? some number, right? Let's say n systems of the same type. Maybe would be the type H in for a certain quantum channel. Then we apply the quantum channel and we send the qubit or the system. So we have a multiple copies. Well, I shouldn't say copies, right? They're just, all we say at this point is that there are systems, that the output of the encoding is 3 systems that are appropriate for feeding into the channel. And then we get, here we get H out, right? And here place here would be n copies of that. And then we have a decoder. And, sorry, this is also all quantum stuff, right? Some wavy lines. So then the decoder makes something out of that, right? And all these are, of course, quantum processes. And now the question is, when T has a certain level of errors or produces certain kinds of errors, can I choose E and D and the number of uses of the channel in between in such a way that the overall channel is better than what I had before? Right? Like in the classical case, this error correction process doesn't completely eliminate the errors, but it reduces them by a large factor. Right? So the same thing is what we're trying here. Right? So certain types of errors that might appear here should maybe completely be corrected. Actually, this is the classical or the standard theory of error correction. But also small errors should become even smaller, stuff like that. Right? So this is, if you want, this is spreading of quantum information over more systems. And this can be done in various ways, but it is not copying, right? So this basic scheme, of course, might make sense, even though, well, this cannot be a copier because a copier doesn't exist. But it could still be something, some device that would take one input and produces 3 outputs. And maybe if this is a d-dimensional Hilbert space, this could be an isometry that maps the d-dimensional Hilbert space into a d-cubed dimensional one. Maybe of the same type, right? It doesn't have to be the same type, but let's assume that. And so we would have a d-dimensional, this would map our quantum information from d dimensions into a d-dimensional subspace of this d-cubed dimensional overall space. So this certainly exists in many ways, but this process does not imply any copy making. Okay, so so we analyze this. So first step. Let us think of this whole garbage as one channel T, and of this second thing as one channel D. Why did I use curly? I think I straight letters for. Right. So let's just take this whole channel, and so it has the property that you start out with some Hilbert space dimension. The immediate Hilbert space dimension, intermediate Hilbert space dimension could be much larger, and then you go back to a small space. And the question is, when can this ever be done, right? So ask, so which channels T have the property that there is another channel, call it D, that will be the decoder, such that TD is the identity. So we're actually looking for right inverses of channels. If we write this in Heisenberg picture, if you write in Schrödinger picture, of course, everything would be, we would take adjoints everywhere, and I would actually be looking for left inverses, right? So, nothing deep here, it's just the way we organize it. If you write in the Heisenberg picture, and you look at such a diagram, then this corresponds to the standard order in mathematical notation for applying functions, which is the argument is written after the function, right? So then it would be like an observable here, and then you have the observable dx, that is this plus the decoder, and then comes t and so on. So if you write in the Heisenberg picture, the sequence on the blackboard will be the sequence on in your formula. If you write Schrödinger picture, you have to invert everything, or convert to Polish notation on your mathematical side, right? So this is actually done in some fields, that you first write the argument and then you write the function. But this is just a convention of how mathematical notation works, right? You could actually do it the other way around, which would be more logical, and then you would have the same property for the Schrödinger picture. But we are not trying to change mathematical notation over at the same time. So, okay, so this is the question we want to answer next, and I think this is a good point in time to get some space.
Why don't we employ errors in this condition?
Sorry?
I mean,
the errors will come. The errors will come. So the t will these t's will contain the errors, right? And now we actually will look at what different kind of errors can be corrected at the same time. So that actually there will be a variety of channels t that are all corrected by the same d.
yeah, but this condition implies that we only allow perfect correction.
For the moment, I'll tell you about correcting small errors. let's work with 2 for the moment. So we want to do this. So this channel T, let's say, is given, and we want to find D such that the whole thing is the identity. Right? So when can we do that? And now T, I stick to the Heisenberg picture and leave it as an exercise if you don't like that, to write the corresponding Schrödinger picture. I think it's actually easy, right? So nothing deep here. So this will have some cross decomposition, right? Where the sum, where if I stick the identity in, I get the normalization sum. That also has to be the identity operator, right? So some ki star ki is the identity. Now, this we can interpret as an instrument, right? So we can read out this information. So the whole thing could be considered in the following way. We have this process T, and if we ignore these outcomes, so this will be corrected if we ignore these outcomes, right? We're not interested in these outcomes, but let us keep track of them anyway. Then still, the overall channel has to be the identity, and the observable, so the observable measure T has POVM elements ki star ki. That is, if I'm not interested in what happens afterwards, this is another normalized channel. So if I stick the identity here, for example, I'm not interested in what comes out, only in this part, then the probabilities for a given input state are given by the expectations of these operators, right? So I consider this channel, which is a general channel, right, as one that produces classical information and quantum information. And I'm looking for a moment at the classical output. Now, we know what this could look like. So this is no measurement without perturbation. Without any big computation, we know that these things have to be multiples of the identity, right? So these kappa I, this is supposed to be a Greek letter called kappa. So these kappa I will be positive numbers. Well, they could be 0, but if it's 0, then actually this whole operator is 0, and we might as well drop it from that sum, right? So you could think of these as strictly positive, or, well, it doesn't matter. And yeah, so these are numbers. And they add up to 1, right? That's some of it. Okay, so this simply comes out, the whole thing is supposed to be the identity, and therefore whatever information is generated has to be non-informative. So, next step is this has to be true. For any Krauss decomposition. For example, for ki prime, which is the sum rij kj over j, where r transpose r is the identity. Right? So if we or unitary actually, sorry, r star. Doesn't have to be real, sorry. Right? So if we make a unitary, remember the Krauss decomposition arises So the Stein-Spring decomposition, or the Stein-Spring dilation theorem, is something that doesn't require any arbitrary choices. Right? There is a unique isometry, unique up to the obvious possible transformations. The Krauss decomposition depends on a choice, namely the choice of a basis in the dilation space. And if you choose another one, we get another Krauss decomposition. But for that one, the same thing has to apply. So if you put that together, so actually this is not just true for the Ki as originally chosen, but also for any linear combination. For example, you could take 2, right? And then you get a cross term from the linear part. The quadratic terms have to be proportional to the identity, therefore also the cross terms. And you could make these coefficients play also with the phases, so this is called polarization. So let me just note the keyword. Because this is true also for linear combinations, we actually get the following. Ki star Kj is some number lambda ij times the identity. And these numbers, yeah, okay, so some just numbers. Now, our aim is still, I erased that, but our aim is still to characterize the t's for which such an inverse operation exists. Right? So the t is fixed, but we can make our life easier by choosing a good Krauss representation. So diagonalize lambda by a unitary transformation, which would be just such an R, and so by choosing R, so we can actually write that. So this is now not necessarily the Krauss operators that we started with, but it might be another set of Krauss operators, right? So Ki star Kj is delta ij, and then for the equal ones, let's still call that kappa I times the identity. So this matrix lambda of arbitrary complex numbers, well, it's obviously Hermitian. I should have mentioned that, because otherwise I can't say diagonalize, right? So clearly, if we take the complex, the adjoint of this equation, we get the complex conjugate matrix, and these I and j just swap places, right? So this matrix is obviously Hermitian. So so we can diagonalize it and therefore bring it to this diagonal form. Right? Now, what does that mean? This means that just think about one value of I. Then that means that this Ki is essentially an isometry. Right? It's up to a factor. It's an isometry. So actually, if we divide by the square root of kappa I get a proper isometry. Which means that the k's in the other direction, multiplied the other way around, so Ki, Kj star, or the Ki star is a projection. Right? So if the, so let's say 1 over the square root of kappa actually is isometric with orthogonal ranges. So the different ones actually have orthogonal range. That is expressed in the zeros here. Right? Okay. So how can we make the decoder? If that is the case, then so we'll simply set di to be equal to 1 over the square root of kappa. Ki star. Okay, so these will be the cross operators of the decoding channel, and let's just check that this works out. So I gave you this isometry argument to tell you about the normalization, and so let's check. But first, maybe the let's compute TD of x. Right? So this is the sum over I, di star x di, and then kj star kj. Right? So this is the overall set of Krauss operators. You see in such a, I mean, of course, the Krauss decompositions can be multiplied very easily. One channel after the other. This will just give a double sum and the corresponding Krauss operators. And we know that this whole thing being the identity, these have to be the identity. And this is why the K star are a good candidate, because they know they just do that. Right? So then di kj, what is that? This is 1 over the square root of kappa. Ki star kj. So this is delta ij. Now not the kappa here, well that gives a kappa, but we have a 1 over kappa I, sorry. So we get just the square root of kappa I times the identity. Now, if those are the Krauss operators, or every Krauss operator, the sum is the identity, we know that this must be the case. Otherwise, we couldn't get the ideal information out at the end, right? So the composition has to have Krauss operators, each of which is proportional to the identity. So that exactly happens here, and therefore we get, this is, so the TD of x. Well, this is the identity, I can pull that out. So this is equal to the sum over I. The delta ij makes this a single sum. So we get the square root of kappa I from here, and another copy of that from the first operator times x, because we commuted this identity through. And so this is just x, because the sum of the kappa I is 1. So those are the probabilities with which the coding spreads into these different subspaces I. And you can also check that this is normalized. Well, this is sort of normalized. It's not automatically fully normalized, because this is normalized to, so the sum of the di star di, right? You can verify that this is a projection, and because the di are, well, they are di star are orthogonal isometries, and that's why. So these would, each one of these would be a projection, and these projections are orthogonal, so they add up to less than 1, right? So this is a projection. But it's all the possible inputs that come from the channel will always end up in the space that this projects to, because that's a joint range of the Ki, right? Onto well, the join of the spaces 1 to whatever K-I-H, right? So the original input space is mapped somewhere into this higher dimensional space, and so each one of these terms identifies this space of the original dimension with one of the spaces in the larger space, and that's what this projects to. Right? So these are orthogonal projections to each of these factors, and then the join of all those will be some projection. And so introduce d naught so that d naught star d naught is 1 minus this sum. So you could normalize, you can also make this a proper channel that is properly normalized. And but this Krauss element, if you think of this also as a measurement, right, then actually if you think of this as also producing a J here, then these values will always be the same. And there is an additional value 0 that we just created that will never occur in this process. Right? So this is just to formally make this normalized on arbitrary inputs, not just on the ones that come out of T. Right? Okay, so here we've computed that it is actually the identity. Right? So the theorem allows a decoding channel so that is a right inverse TD is an entity, right? If Ki star Kj is a multiple of an entity for all I j. So then you can do this diagonalization process, and actually this diagonalization tells you how the decoding must look. You have to sort of organize that. Well, no, you just diagonalize and take the d's that you get out of that for the decoding channel. So this is actually known as the Nil-Laflamme theorem, right? And what it tells you is sort of the inverse. No disturbance without measurement. Well, this gets a bit confusing, but measurement. It's sort of the inverse of this no measurement without disturbance statement. What it says is, let me just, this is confusing because there are too many negations in that and you have to get confused. But what does it say again? So if you have a channel that can be corrected, right, then its outputs in arbitrary bases, right? So there's no way that this channel could act and produce some information for the outsider. Right? So these channels have the property that whatever measurement is consistent with the overall channel action will be non-informative. So there's no, it will never produce any kind of measurement, and this is the kind that has no disturbance in the sense that the disturbance can be completely corrected. Right? So if we had the other statement that if you have a channel that well, is it really inverse? I feel it's sort of an inverse. These phrases don't help to logically establish what kind of inverse that is. So these channels are ones that don't leak any information to the environment, and those are exactly the ones that can be corrected. So let's just stick with that equivalence. Right? Okay, so how does this work in practice? So the encoding is done by an isometry. Let's say V from H to, now let me just write H in tensor n, right? And H in is the input Hilbert space of the channel that we're actually using for the transmission, which has the many copies of T now again, right? And then, so this is the encoding. So the channel acts with cross operators EI, let's say, and the jargon calls these error syndromes. So, for example, well, EI tensor identities. So these are the EI are the cross operators of a channel, and we think of these as possible errors. One of them being no error. So maybe E naught is the identity. That is the case when, for example, we choose that. If the channel has an E naught component, then sometimes there is no error, right? So this is a special case of error, but actually you don't really need that. But typically the errors would be localized on one of these channel uses. If you think of this in terms of discrete error correction, very much along the classical lines, right? And then, so this is that maybe call this error EI at K, at place K, which is, this is kth place. Right? And then applying theorem to the operators, so the family of the Ki for this channel would then be EI K, right? Little k. So this collection of error syndromes is then the set of cross operators that we have to live with. Now, one of the features of this is that if this condition is satisfied for one choice of these cross operators, it automatically is also satisfied if I replace any one of these operators by a linear combination of the same operators. Right? And then get the corresponding linear combination here. Right? So simultaneously correctable. So if I have any channel, or if you want a slogan, the set of correctable syndromes forms the vector space of cross operators. So if you can correct, for example, a Pauli X and a Pauli Y and a Pauli Z rotation, and the identity, which would correspond to no error, then you can correct every error. So there is a finite number of things that you have to check So this equation here has to be checked for a basis of that space of correctable syndromes. And if you can do that, you can build your decoder in terms of that. And then you see that also if you take what the essential property that we need is that if you look at the combined cross operators, the dikj things, all these have to be multiples of the identity. And that will be true if I replace the ki by a suitable linear combination of them, right? Only the values of the linear combination will change, but the complete correctability will just remain the same. So if you build channels, that is automatically correctly normalized, from these cross operators, you will get something that will be completely correct. Right? So example, so there exists a code B from 1 qubit. So we're just doing error correction for 1 qubit and into 5 qubits. So the Hilbert space would be n is 5, right? And which corrects arbitrary errors on single qubits, right? So the overall picture would be, well, you have a description of the errors that will be completely correct. This is correcting rare errors, right? So let's say your error channel, the channel that over which you send, has one large contribution, let's say 1 minus p times the identity, that's the first, or square root of that, is the first Krauss operator. So this is, then if that is applied, if you want, all is good. And then there may be something else, right? So this will be a small contribution. Now if we then write out the overall Krauss decomposition of this, then we see all the errors that involve where you have at most one of these bad guys in each factor. The total weight of that, I mean, all of these will be corrected completely. But if you start looking at the terms with more errors, I mean, if you just expand there's a cross sum for each of the channels. So of course you have cross terms where there are multiple errors happening, right? But these will then have quadratically small. At least you need, if the overall coefficient of these terms is small, then you will have the square of that, at least, in the overall channel, right? Because the linear terms, where the error probability enters linearly, will be corrected away, right? So there is a process by which you can turn this idea of error correction, which is in some sense the correction of rare errors, right? So on one of these 5 qubits you can have an error. And then you will see nothing at all in the output channel. But you could convert that to a statement about small errors, right? You have a channel that is close to the identity in a suitable sense. We'll talk about that. And that means that you can write it with one big cross operator proportional to the identity and other stuff. And the other stuff is somehow small, and then the overall norm of the other stuff will enter quadratically, very much like it happens in the majority vote classical error correction, right? So your overall error probability goes from p to p squared. The difference in the quantum case is that there are more kinds of errors because you have to have, apart from the identity, you have Pauli x, Pauli y, Pauli z. So you can't do it with majority vote on 3, you need 5 qubits. This is a perfect exercise, actually. So I'm not too keen on working out all the products that are necessary for doing this, but well, maybe I'll do that tomorrow. So I'll show you the 5-bit code, and then actually I am interested in doing small errors. So there was one request for what we want to do in this channel, which is semi-definite programming. So this is my route towards that, right? So we have to talk about how to quantify errors. So this will be the next chapter here. So what are the quantitative error criteria? And in the end, if you know what the noise is, for example, and this is actually in technical application, this is the case. You know exactly what your channel does, right? So you know what the noise is, and then you might actually adapt the encoding and the decoding in such a way as to optimize the overall transmission. And but then optimizing needs a clear numerical target. You have to say what quantity you're optimizing, and we have to talk a little bit about what they are. So I'll talk a little bit about norms, and then the way to compute that, to find the optimal coding and decoding, is actually a typical semi-definite program, and then we'll talk a bit about semi-definite program. That will be the next couple of lectures. Okay? So thank you for your attention today. See you tomorrow.